So what makes this the best?
Well, there are 5 points, starting with accuracy. You know how frustrating it is when your miter joints end up with a gap. Doesn't happen with this miter fence. Then there's of course the clicky action. A positive stop every half degree that you can count on. Third, the locking feature. Within a second you can go from locked to unlocked. And everything else is pure user friendliness. A big scale and knob for easy adjustments also in between the lines, quick action levers for clamping, and a guided fence rail that will never give you headaches with T-nuts. And then of course the noise.
So satisfying. I built it for my homemade oscillating belt sander, but it would work with any other T-track this size. Making it to 0.1 degree accuracy was challenging but fun. Raking tools, combining old and new technology, and collaborating again. Let's jump right in. And I'm gonna start with the miter bar, which starts out as a piece of 20 by 10 mm aluminium bar.
I only need a small section of it though, and my best friend, the hacksaw, is right there helping me.
Now like this, it's too wide for the channel, so I have to cut it narrower and also add a few features, which I'll do on the CNC router. But in order to mount it on there, I first need some holes.
And they need to be positioned relatively precisely. Here, here, and there. Then spotting, drilling, reaming, the usual. Now at the CNC router, I can use some dowel pins to align the part perfectly with my hole grid and bolt it secure. There aren't many operations necessary, and the first one is the outer contour that cuts the part to length and width. Next is the roughing of the little pockets, followed by the contour that cuts them to size. Then tool change to the chamfer bit to, surprise surprise, chamfer the part. And right after that, spot all the positions for holes. Chips removed and I can check the fit with the T-track. Looks good, so I can flip the part around to cut the feature on the other side, which is another little pocket. Turned out very good so far, but there are still some sharp edges which, believe it or not, you can just chamfer with a woodworking router bit. Okay, now I can punch the spots a bit more and drill all the necessary holes. We have many M4 threads, 2 counterbores to a specific depth, and a countersink on the other side. And the main pivot hole that gets pretty fine threads. The last 2 ones are in the edge, but that's easy because the part fits through the table hole.
What a great start, and it also remained very straight. Indeed not perfect, but good enough for the application.
Yeah, right after that I skipped one side on the CNC again, which not only made it shiny, but also ensured it sits below the T-track surface.
It fits with a little bit of play by design, because in these pockets there now go some plastic split rings, and when I tighten the screw, they expand and let me adjust the play and friction. It's a pretty common way of doing that, so common in fact that I could have bought the whole rail off the shelf for little money. Ah, shit. But I still would have had to drill all the custom holes, so whatever. Let's move on. Now something that rotates obviously has round parts, and I'll tackle the most complicated one first. We have 2 precise diameters, a through hole, 2 custom threads and a flat. That'll take a couple minutes.
At least it's small, so I can use up little scraps. After I clean up pass, I can start with the different diameters. I probe the front surface and all dimensions start from there. Switching the feed direction makes this whole process also a lot simpler. First, the precise 10 mm diameter. Next, the outer diameter for the threads. And then the 8 mm diameter. A chamfer for everything, and I can switch to the threading tool.
Now to achieve the 28 threads per inch pitch, I need to change the gears on the lathe, and on this table 28 tells me these 2 gear pairs.
In theory, you just need to find the right gears, install them, and go. But in reality, this is time consuming. And I only do it when I really have to, because this can also happen.
And I've assembled it the wrong way. This needs to be inside. I love doing things twice. I also run the lathe in reverse and feed the tool out, which eliminates the risk of cutting into my part the wrong way.
Quick check with the scratch mark. Looks right, but the pattern is kind of uneven. Hopefully this doesn't cause problems. So let's go.
Weird. On the third pass, the tool didn't seem to hit the same thread again and cut a new one. I guess that means I cannot disengage the feed lever and move the sled, because then it will be out of sync with the thread it's cutting. And that also means the part is garbage. Yay, starting over.
Back with a new part, and I cannot believe I did this.
Fuck.
No disaster, I can continue. Just don't do that with the deeper cuts. Well, something told me I need more practice. At least that's what this part is still good for.
Alright, finally. Well, I still screwed up the part because I fed in the wrong direction again, but at least I now know the threading workflow. But what's also weird is that the pitch that I'm getting is kind of uneven. I guess the only thing that can cause that is the lead screw or the split nut that engages with the lead screw. I totally did not want to disassemble the lathe, but let's have a look. All right, access to the split nut. Yeah, that's a bit dirty. But after cleaning them, there wasn't anything super obvious. One had a pretty thick layer of gunk embedded in the threads, which maybe prevented it from closing all the way onto the screw. In terms of wear, you can see it here a bit, and it's also uneven. But again, I don't know if that's a problem, so let's put it back together.
Obviously with some fresh grease.
There's also an adjustment screw that sets how far the nut closes, and maybe due to wear, it cannot close all the way anymore.
But that's an easy adjustment. Let's see if any of that helped.
I'd say slightly better, but not good. If you have any other idea what it could be, let me know in the comments. I'll now continue as is, because I have to make the part. Again.
And this time I also left a pretty large relief cut to start the thread. No more hiccups.
Ah, finally.
But that was just half of the part. I still needed a through hole and threads on the other side. And if I feed the wrong way there, I will definitely crash into the chuck. But it went well.
Almost no play. Nice.
I could finish the lathe work and move on to make the wrench flat with a little belt sander. That brought a smile back on my face. What a journey. And while at the lathe, I also turned 2 additional parts for later.
But so far, we've only made a bar and a shaft. For the accuracy I'm going, it was important to make them precise, but we need to pick up the pace now.
So next are the parts that actually pivot and hold the fence rail. They are 8mm aluminum plate, and I could nest them to cut everything at once. But the center hole I prepared on the drill press, which I then used again for positioning on the CNC bed. Let it rip. Not that kind of rip. Let's try a different cutting strategy. Doesn't look too well. I see, wrong bit. Now it's good. So first roughing and finishing the curved slots. Then the contour of the brackets with 0.3mm thickness left, and same for the big contour. Then tool change for the little pockets, nothing special here. And next tool change for chamfers and spotting holes. On the scroll saw I could then cut all parts free and finish them at the router table. Not everywhere possible for the small parts, so I finished them with the rotary tool. The threaded holes are straightforward, but the center hole is different. I located it with a pin, open it up to fit the counterbore, and finally reamed it to 10 millimeters.
And the shaft from before fits in here nice and perfect.
So this is done, as well as the little brackets. Last piece missing is the front bracket, which I could cut to length at a table saw. And I guess you can imagine how I drilled the holes. On the CNC router, I also machined one surface flat, because the raw material itself wasn't flat enough as a reference surface.
Now only those two surfaces will contact the fence rail, which are now nice and precise.
Time for some assembly using screws from my now colleague Stefan from CNC Kitchen. Check the description for more info.
The holes in these side brackets are oversized, which gives me adjustment in this direction and this direction. And then tighten down, very solid.
But one thing I don't like is this. Too much friction. So I bought some low friction Teflon tape to stick to the underside and then cut it flush again with this handy little tool. That's better. On top goes a tightly fitting 3D printed nut that applies just a little bit of friction.
Okay, that's the solid foundation. Next comes the part to actually set and adjust an angle. And to do that precisely, I intuitively want this to be a knob to turn. Because on a lathe, you also have knobs to do fine adjustments or to set the table saw blade to an angle. There's a hand wheel. It's a motion where you just have good control. But what we usually get with machines is this or this, where it's more of a guessing the angle. And I get it, this is cheap to make and suitable for some applications, but I don't want to build mine cheap, I want to build mine good. And probably the best way to turn a movement here into an angle adjustment here is with a gear.
Something like this, and thanks to 3D printing, I have it and the matching knob only an hour later.
But unfortunately, there's a problem. When I look close at the teeth, I can see they are the wrong shape. It's all rounded and just doesn't have the shape of the model, which can cause improper gear meshing, so either it's not running smoothly or there's play, so backlash, and we cannot have that here. It may sound ridiculous, but for the accuracy I'm going, it's not working. Well, and that's just the limit of this printing technology. This geometry and details are just too small. So we need to move to a more accurate printing technology. This part was printed on the Formlabs Form 4 SLS printer, and the parts it produces are incredibly detailed.
Unlike a filament printer that builds the part by extruding melted plastic from a spool through a moving tool head layer by layer, the Form 4 uses a tank of resin and cures one layer all at once with UV light and an LCD screen as a mask. The high resolution of the LCD screen and a significantly lower layer height directly translates to the resolution of the parts. After printing, you have to wash off the excess resin with isopropyl alcohol, which happens in a neat washing station. Then washed and dried, it has to fully cure with more UV light in the curing station. And then you have a beautiful part.
But there is a learning curve that I learned the hard way, especially with print orientation. Printing flat on the build plate works, but the first few layers get squished a bit for proper adhesion, and that changes the shape again just a bit. Printing like this on supports was suggested by the software, but this then caused a steep overhang on the outer teeth and also a wrong shape. So what I did was print it flat but on supports, so the squishing happens in the supports and doesn't affect the part. And removing the supports is quite simple. Uh-oh. Usually it's quite simple. I may have overdone it here. But I also have another new tool that should be just the one for this.
You've seen it before, the Proxxon Microsonic Cutter. A small knife swinging at ultrasonic frequencies, which cuts through the supports quick and without applying any big forces, so I'm not at risk of breaking my part.
But that's not all it can do. It's great at cutting basically anything like other plastics, the tape from before, or just cardboard. It looks so fake, and yeah, any other knife could do this, but it cannot do this. A clean cut through a 3D print.
Here another one slightly sped up. And where it really shines is in cutting carbon fiber, because it does it with producing almost no harmful dust. I will primarily use it on removing support structures, for which I can also choose between 3 different blades. For example, the saw. Now it's free, and the scraper is perfect at removing the tiny leftovers. One thing to keep in mind though is to keep all components, which are the blade, the bushing and the bore, clean, so the vibrations go trouble-free into the blade.
I had even more uses during this project, and for your out-of-the-ordinary cutting jobs, check it out in the video description. Neat little tool.
Now the nice cleanup wasn't strictly necessary for this specific part, because I printed it oversized and now machine it to thickness.
It's important to mount the gear centered in here, so the circle center of the gear is in the pivot point. That's not too hard, but I need a jig. Okay, next comes the knob with gear and the shaft it's pivoting on.
For the shaft, I have 8mm precision ground material, but the end needed to be slightly larger, so I turned it down a bit and made a bushing to hammer on. Like this, I can turn it down to size. Machine the threaded hole in the end and cut it off. Now the other way around with the center, I could turn down the section that got threaded with M6. The perfect use case for my threading die holder. The actual adjustment knob is another resin print. And straight from the curing, it goes into the lathe. Like the gear, I printed it oversized on supports and now machined all the supported surfaces to dimension, so they fit a small and a big washer. And then reaming the center hole. Flipped around, I could turn the recess to dimension, which needs to be exactly 45mm. And then I could mount it to a mandrel to turn the recess into circumference, which will make sense later.
That turned out really well. Let's test the fit. It fits, but it's a little bit on the tight side. Pretty cool. I would like it to be a little less tight, but for now at least that means there is zero backlash.
Making it less tight is possible with a property called profile shift. The gear generator I'm using calls that backlash, but what it does is changing the tooth size without affecting the general shape. That works in both directions to make the teeth either smaller or bigger. So I printed new gears with 0.1 and 0.2mm profile shift and improved the support structure settings.
That's the 0.1mm backlash. Let's see if that's good. No, still a little bit of resistance. So now a 0.2mm backlash. And that's good. Nice and smooth all the way. And no actual backlash. But even with it working well now, what caused the adjustment to be necessary? Well, the prints may not be 100% accurate, or the hole distance of the two shafts isn't spot on. And with these two positions fixed and this gear size also fixed, I could only custom fit this gear. In hindsight, it would have been better to design adjustability into the hole spacing. Much simpler than printing custom gears. All nice and well, but so far, in terms of accuracy, this isn't any better than this one, just more fancy. And for the accuracy, I don't really want to rely on reading a scale. I prefer positive stops that I can rely on. Like the ones I built into the actual sander. One for 90 degrees, one for 45 degrees. But on here, why not have a positive stop for every degree and make this behave like this encoder hand wheel from my CNC router. And every click would be a degree. So yeah, basically this in here. Well, and that's the exact purpose of this groove and this print.
So let's free it from the supports again and turn it to a matching fit with the 45mm diameter.
Now I have 120 little teeth around here, a number I didn't choose randomly. Also note the gear ratio, because one full turn will move the fence by exactly 60 degrees, and so one click of a tooth will be half a degree. Which means I will have positive stops with half degree resolution, 60 degrees in either direction. Pretty cool. Well, at least if I can make the next part.
And that's the clicker pin, because the part that interacts with all the little teeth is a precisely guided, spring-loaded ball.
I've got a 3.5mm steel ball, the matching reamer, and confidence to succeed.
It started with another small piece of shaft that I first turned to length. Then it needed a 3.3mm through hole, which is also a good starting size for the reamer. But with it, I need to stop close to the end to leave a little bit of material behind. Looks like it worked.
Dropping in the ball, it doesn't fall through, but sticks out. Good sign. Even better when I seal the end and drop it in. You can see it falling slow from an air cushion. And that means the hole is pretty precise.
Great, so I can finish the part with chamfer and threads.
But something's still a bit off. Now ball and spring go in, and then a screw where I turn off the end so it can apply pressure to the spring at the same time. Ooh, this is already promising. On top now goes a washer, an O-ring, and a lock nut. It's not tight, but compresses the O-ring a bit, so there's a small but constant downward pressure. So satisfying. It's not just the noise, it's also the feeling. It just feels, I don't know, precise. The amount of positive stop, or how hard it clicks in place, is also rather decent. When it's clicked in, I can wiggle here a bit and nothing moves. It feels like solid, if you know what I mean. Pretty cool, especially on the first try. I honestly expected to build this clicker pin like 2 or 3 times. But I'll take it. And next, I want to improve the grip. Ideal would be a newel, and I could have printed it in place, but instead I made it this channel because I wanted to experiment with a flexible newel.
I also have some flexible resin for the Form 4, and this should be the perfect use case. Somehow it's weird printing a flexible part from a liquid, but the detail is phenomenal. And I printed a finer and a coarser one. It's slightly undersized to tightly stretch around the knob.
Oh yeah, I definitely like the coarse one better. Not even gonna try this. So now I have grip and precision, but I still need a scale to see what angle I'm at.
Putting it on the knob surface seems ideal, since it's big and will be easy to read. Another part for the Form 4. But right now, you can't really see anything. Just wait.
The level of detail is phenomenal. Here the resin printer really shines. For comparison, a multicolor filament print, all the small details like these tiny arrows just aren't there. Here everything is sharp and crisp, and the line width is just 0.3 millimeters.
Later I also experimented with an inlaid scale, filled it with paint and sanded it smooth again. But that was quite tricky to get right and took many attempts, so for now I stuck with the Sharpied version. It gets mounted with M2 screws and nuts, which are embedded underneath the clicker ring. And there's also adjustability built into the scale. Now the pointer, fresh from the printer on supports.
Oh, by the way, I made this part twice because I somehow forgot that I need to be able to reach the screw.
But with a slight modification, I can now mount it from below.
To get the scale centered, I turned another jig from some scrap that fits the bore of the knob, and just by placing it, the scale now is centered, and I can make sure the lines mesh. The screws are tight, and that's the scale. Just as planned, one click indicates half a degree. And with the veneer scale, I can set 0.1 degree increments. So this is 80, meshing the next two lines is 80.1, 80.2, 80.3, 80.4, 80.5, which is the next click, and the same as meshing the middle lines again. I also included these arrows that indicate which color to look at depending on the direction. So if I want to go to 40, I know black color turning this direction. And let's say I want 42.3, 41, 42.3. This has got to be one of the, if not the most precise things I've ever made, and it freaking works. So cool. But despite being able to set a really precise angle, there's no way at the moment to lock it in place. But that comes next. I don't want to go with the approach of other manufacturers with a twist knob or a twist style lever, because there's the chance that when you tighten this knob, you ever so slightly move the fence again. From my more recent videos, you know I'm a big fan of these cam lever clamps. So no surprise, I'm using them again.
But they need a slight modification. Actually, two levers that need the same modification. A threaded hole for a tiny set screw. That's all, so back together it goes.
Cannot reach the set screw.
Fortunately, there's a second side.
And now I can reach it. And so on top now go the washer, this little turned part from before, and the cam lever. I want it to be tight in this position, which I can achieve with the built-in adjustment ring. That feels good and solid. And to keep it in this orientation, I can lock it onto the threads with the set screw. Pretty cool how many functions are now integrated into the knob. Fine adjustment, positive stops, scale, and part of the locking mechanism, which I think is pretty clever, because once I'm at the desired angle, this not only locks the angle bracket to the miter bar, but also the rotation. This is quick and 100% user-friendly. But now some of you probably say, I just made the same as the cool saw stop miter fence, and I would be lying if I didn't take inspiration from that. But now comes a feature that lets this stand out.
It involves the second cam lever, this part from before, and this part, which I'm not entirely sure on how to make yet. But facing some stock and turning it to diameter seems like a good start. Then I used the threading tool to mark the 40mm diameter circle. Cut the M6 threads and cut it off. For the other side, I put only light pressure on the chuck and run a tool holder into the part at low RPM, which removes the wobble. Then tightened properly, I can face it to thickness. Pretty easy method and pretty good results. Now the part goes into a tool holder, so my lathe can work as a part-time mill again. Done on both sides, I could plunge a bit deeper and make the cut up to the circle mark from before. But that's it with the cool setup. The rest needed to happen with files. Well, except for deburring, there I have better equipment now. Overall, very good result. One more part before assembling this. A shaft that fits through the pivot pin and threads at both ends.
Okay, they screw together, go through the hole of the center shaft, and there it has two stop positions.
I don't want these parts to come apart, so I'm welding them together. Since this isn't my first welding project, I'm feeling much more confident. Oh no, not this again. Well, it's been a while, I'm out of practice and a bit nervous since these parts were time consuming. A good excuse, I think, when it happens just once. Let's try again. Yeah, that's better. Maybe a little bit more heat. Ah, come on, damn it. I'm burning through my tungsten quick. Okay, now it's just getting silly. Finally. Well, it shouldn't have been this hard, but at least there wasn't any noticeable distortion and I can easily hide my boo-boos. Look, a perfectly shiny part ready for assembly.
And this sleeve and the cam clamp, which I lock at this position, so it stops at roughly the same position on the other side. Like this, I can drop it into the T-track on the machine, go to this position and adjust the cam lever until it locks. Locked in this position, it's solid for stationary use, and unlocked in this position, it's movable. Can just switch back and forth. Why? Wow, that problem took me a while to figure out and I was afraid I screwed something up. You can see this part moving when I unlock the cam lever, which creates a gap that's necessary to rotate into the T-slot and lock it again. And it obviously works, but why not a minute ago? Well, I eventually noticed the set screw I installed catches on the plastic here as I'm opening it, preventing it from dropping down, and instead lifts the cam lever a bit. This gap shouldn't be there. What a pain to figure out. Fortunately, easy solution.
I could go in with the microsonic again and cut a relief.
Now it works. Good. But unlocked, it's still loose.
But that's what these two holes are for. Two set screws to clamp against.
Like this, it clamps to the T-slot. Like this, it clamps to the set screws. And this feature, just dropping it in from the top and easily lock it, but still being movable if needed, while never affecting the angle, I haven't seen before. 100% user-friendly.
And although I made this to use with the belt sander, I could use it on any other machine that uses the same T-track rail. Say on the bandsaw, the router table, or especially the table saw. These machines need this T-track installed.
But I'm getting ahead of myself because this is still missing the actual fence rail.
And that's a common off-the-shelf rail with off-the-shelf knobs and T-nuts.
This is functional, but I don't like the scratching around on the table. So now comes the last user-friendly or more luxury edition.
To reduce the scratching, I can install the same Teflon tape from before and cut it perfectly flush with the microsonic.
That's better, but I would like to ever so slightly lift it off the table so it's not even touching, like its mounting bracket. Also, when I change the angle, the rail needs to slide in and out a bit, and eventually this will happen. And I hate it.
But I think I can solve both problems with a single part of brass. With some tailstock support, I can turn it down until it fits the fence slot with about 10 microns clearance. Then I part it off and cut one side flat. With that, it's easier to drill the two M4 holes. Back in the lathe, I reduced the diameter between the holes a bit more, so only the ends are touching the rail slot. About like this. Lastly, I willed down the ends until it perfectly fit in between the T-nuts and prevented them from spinning.
The perfect fence guide. Well, except that aluminum and brass don't go together well because of galvanic corrosion.
That I could solve with some thin washers made from some shim stock acting as a barrier.
To set the small gap to the table, I have it a bit loose, put it on, put two feeler gauges under both ends, press down and tighten. That's it.
And now to crank it to 11, I cut short pieces of spring and put it on the threads so the knob doesn't flop around when loose. One more user-friendly detail.
Now it doesn't matter anymore. Okay, we are almost done, but there is a problem I hoped wouldn't be as bad. But the 3D printed clicker ring is already showing signs of wear. Sure, I'm playing with it all the time, but sooner or later the part will fail. And it should just be made from steel. So let's do that.
I had some laser offcuts from a friend that would be suitable for a ring. I just needed to hog away a lot of material.
So far so good, but now for the teeth I need a mill. And I have no mill, but I know someone with a mill. Stefan Gotteswinter.
Hey, welcome back.
If you've looked up anything about machining on the internet, you will probably have stumbled upon Stefan's channel or blog posts. But if not, you only need to know that he does a ton of high precision machining on small parts and knows what he's talking about. Exactly what we need for the clicker ring. I brought 2 ring blanks, and just for fun, we started by putting them on the surface grinder to correct the 10 microns they were out of parallel. Then he set it up parallel on the rotary table and proceeded with drilling the 6 counterbore mounting holes. For the teeth, he tilted the mill head to 45 degrees to use a regular end mill for the 90-degree tooth shape. Next, setting up a dividing plate for the 120 divisions and start cutting. Once set up, it was a relatively simple process. Move the index pin to the next dividing position, which rotates the part. Make the cut with the y-axis up to a certain depth set with the DRO, and repeat. About 15 minutes later, it's all done and looking good. A quick deburring, and we can check the fit. Perfect. And the sound. Beautiful.
I could do this for hours. But what I haven't been looking at, is it actually accurate?
So I set it up with a good machine square and Stefan compared with an angle protractor. Spot on.
Now I set it to 45 degrees in this direction, which shows as 135.
Okay, let's see. Yeah, that's 45 right on the line.
And now I set up a random angle. Stefan will measure it and then I will show you the scale.
That's 66 degrees and 12 arc minutes. That's without using a calculator, 66.2 degrees.
Okay, but since the reference on here is 90 degrees and not 0 as here, the scale should now show me 113.8 degrees. And it does. So it actually is accurate. Quite a relief, because all this time I just hoped. But now to see the actual good numbers means everything I did is accurate, including the 3D prints. Very cool. Thank you, Stefan, for making these 2 steel versions of the clicker ring. Yeah, 2 of them. And yeah, he also is this tall. I'm pretty short.
You're very welcome. Enjoyed very much working on these parts and bringing...
He's playing with it all the time.
this together, and also finally meeting you in person and having a good day in the shop. And
yeah, we had great shop talk.
Really good.
Awesome, but now I have to get back to my shop, because there's still one operation missing.
And that's to cut a 30-degree chunk out of the fence rail to get closer to the belt at that angle. So setting the fence all the way to that angle.
What? The screw head's hitting the knob.
Well, easy fix. Now it's the full motion. And so now the first use of the miter fence is actually to sand into itself. How poetic. It's taking a good bite, but there's more to go. Pretty good. Switching to a finer belt to smooth that a bit more. Fantastic. A little deburring to break all the sharp edges, which there are quite many. Then also breaking the edges on the other side. And adding the last piece, a 3D printed end cap. Final check for square. Good. And good.
It's done. Let's use it.
A simple piece of wood for starters. Looks good. Now let's check the angle accuracy. First in this direction. And in this direction.
Oh yeah, no gap. And achieved with the 2 different 45-degree positions, I would call this reliably accurate. I need this for the table saw. I'm sure some of you would even like to see this as a product, but like this it would be very expensive, and that's currently not what I want to do. But if you want to try to replicate it, you can get my 3D files, check the video description, and give it a shot, or heck, just 3D print the whole thing. Last question, should I paint it? By the way, I still haven't heard back from all winners of the giveaway from my last video, and now I had to pick new winners, so please check your